Hey, Year 12s, welcome to Thursday's Double. Today we're going to take a look at exercise 9.5, and that's on transition matrices and recurrence relations. If you haven't done exercise 9.4, please do not listen to this and do 9.4 like all the questions, or else this won't make any sense. For those who have done 9.4, just remember transition matrices tell us, I guess, a trend of movement from one week to the next. If you recall from financial maths, recurrence relations just mean finding the results one after another. So one step after another. So we spoke about money and interest in years, and if we were to do it recurrence relation, it'll be week 1, week 2, week 3, week 4, okay? And there's no way to jump that process. So what happens when we combine transition matrices and recurrence relations? Well, if you go back to 9.4, our transition matrices were pretty basic. We could only find the movement from one week to the next. So what happens if we want to find out the movement from week 2 to week 3, and then week 3 to week 4, week 4 to week 5, so on and so forth? Well, this is where recurrence relations come in. There's a lot of, I guess, jargon. I promise you it's not as complicated as it seems. So I wish I had you guys in the classroom so we can ask questions, but I'm going to do my best to see if I can cover all bases. And remember, if you have questions, please send them through. Don't be shy. So just to start with, just to recap on transition matrices, we had a look at an example last time on the number of shoppers at Eastworld and Highton shopping centres. So this 75% who shop at Eastworld, and then so they shop at Eastworld one week and then shop at Eastworld the next week. This corresponds to the top left element, and we convert the percentage to 0.75. Remember, the columns always add up to 1 or 100%. So if the top number here on the top left is 0.75, 0.25 is going to be the bottom left number. This part here, 90% of all shoppers, or 90% of shoppers who shop at Highton one week will shop at Highton again the next week. So as we can see, Highton appears to be more popular. And this piece of detail tells you where it goes in the transition matrix, which we call T. Now, suppose that we know that this week there's 2,300 shoppers that go to Eastworld, and 12,000 who go to Highton. What we can do is we can create a matrix, which we're going to call, I guess, our S0. You're going to learn that later on. So this is what we call our S0 matrix, which is what we start with. Initially, there's 23,000 shoppers at Eastworld, and this is how this matrix came about. And 12,000 that go to Highton. So with these two pieces of information, and with matrix T that we took from above, when we multiply the two matrices together, we can say, or we can tell how many people are going to go to Eastworld and Highton the next week. So the next week here we have 18,450 shoppers who are predicted to go to Eastworld, and then 16,550 shoppers who are predicted to go to Highton. Okay, so this part here correlates to the prediction. So the answer of multiplying the transition with the starting amount of people. Okay, I'm hoping that's making sense. And so from there, we can actually start building further predictions. So let's give me some time. I'll try and highlight. So this part in orange, predicted to go to to Eastworld. This part in, let's go with orange and red. Predicted to go to Highton. So remember, with recurrence relations, once we figure out one week, we can use this value and replace it and figure out the next week's as well. So this This matrix here, that's secondary to the transition, is always going to be constantly changing. Right. So this transition matrix is still the same. Let me just color coordinate what's going on before we explain. So that's after 1 week. Now to figure out what's after 2 weeks, we take this and we plug it in again, and then this will tell us roughly how many people we can expect in week 3 at Eastworld and Heighton. So I'm hoping you guys are kind of getting the gist as I'm running out of colors to shade these values in. Please take the time to watch this video and don't just skip through it and be like, oh yeah, I get it. I can guarantee you there's probably going to be issues where you go and realize you may not. Oh, that's kind of similar. We can't have that. Maybe we can use this like dark green. That's kind of gross. Yeah. Oh, but now we can't see the words. Why aren't there more colors on the palette? Dark green? Maybe this green. Yeah, that works better. All right. And then what we've established is a relation. What we started with, 23,000 at Eastworld and 12,000 at Heighton, is what we would call the initial state matrix. Just like in recursion, when we had the V0 value, this is basically the starting point. Okay, so the S0 is what we call the state matrix. That's the start. And then Sn plus 1, notice how recurrence relations always has that plus 1 because we're figuring out the week afters, and we take the transition matrix and times it with, I guess, the answer from before, which is what's happened in the secondary one, as we've just shown above. Again, this is pretty abstract. Once we get into the examples, I'm hoping it'll make more sense if it doesn't already. The general rule, we'll leave it for now. It's probably going to be pretty gibberish to you looking at all those, so please don't dwell on that. The CAS steps. The CAS steps we're going to take a look at. So to create these sort of transition matrix in the CAS, obviously you don't need the T equals and this week, EH, and next week. All you need to do is just be able to construct a 2x2, and you need to be able to store that as T. So what we do is all that above that we just did is doable on the CAS, right? So you never want to do this stuff by head. And we go into creating our matrix, that lol squiggly circle button. Click on that and you can generate the matrix that you want and input the values. Once you do, there's no like S and a little 0. You just have to input S and a big 0. It's going to look a little bit funny, but that's the closest thing we can get to the S and the subscript 0, which is that one there. All right, so that there is corresponding to the S0 right there. And all we've did is just pressed control variable and the store button to get the little arrow there. All right. After that, you got to create your transition matrix T, and store it like so. And once you've got it stored, you can input the next line where you go T times the S0, and you call that S1. And then you can do that over and over again to get your S2, S3, S4. All right. Now, just trying to think what sort of issues you guys might have. The issue might be regarding the arrow. So remember, if you press control variable, that'll store it. And then once you do the questions, you got to delete it. All right, so like clear A to Z. So press menu. I think it's like 1 actions and then delete A to Z. or delete all variables. So then the next question, if it uses S again, it won't have the matrix that you used previous questions stored in the cows. What other questions could you guys come up with? Remember, when we're talking about people, you always want to round up. Okay, regardless what the decimal place is, you always want to round up, because if you have 0.1 of a person, we can't just shave off 0.1. We have to go up, just in case if there is a chance that that person does rock up to the shopping centre. So you always want to bump it up if you're talking about shoppers or people, or trucks or anything that's tangible that you can see. Yeah, okay, I think that's all the questions I can think of. Now, here's the state matrix rule, which just shows, remember like recurrence relations back in chapter 7, when it went through all the generic stuff? This is what you did in the CAS, all right? So don't worry again too much about this, because we're going to cover all this in the example, and hopefully it's going to make sense. And then you can go back and be like, oh, so that's what the formula meant. If the example doesn't make sense, you need to email me and let me know, because again, you guys are very important. You are probably the most important students, as well as my Year 12 health students, since this is your last year. So my priority goes to you. Please ask questions if you're unsure. Anyway, here we've got an example that's pulled from, I think, exercise 9.4 as well. Not sure, but what we're dealing with is a fleet of trucks which start in either depot A or B at the start of the day, and by the end of the day, the trucks end up at either depot A or B. So if you think about a truck company, if you have a station out west and a station out east, and if you had to do a delivery all the way out west, let's say Warrnambool, well, you're not going to drive past the western depot and store your truck back in the eastern depot per se. You'll probably just drop it off at the western depot, even though you were initially in the eastern depot. So that's what this sort of scenario is talking about. So at the start of the day, if a truck started out in depot A, and this 0.95 basically says there's a 95% chance that this truck will return back to depot A, right? Mainly because maybe all the deliveries are out towards depot A's side anyway. All right, if a truck started out in depot B, there's a 15% chance it'll end up in depot A at the end of the day, or at the start of the next day, so on and so forth. So here what we have is the question. At the start of a particular day, there are 40 trucks at depot A and 100 trucks at depot B. What is this information called? If you said this is our S0 information, you are bang on. All right, so this is what we're going to highlight in yellow. This is what we call our S0, or our initial starting point. Never forget that. After 6 days, well, the question says, how many trucks are at each depot after 6 days? So 9.4, we could only figure out how many trucks were left after a day. 9.5, we start talking about 6 days, 7 days, 8 days, 9 days. But don't worry, you don't have to do a recurrence relation. Just like finance, there's a recurrence relation formula, and there's also a any day or any value formula, if you recall. Hopefully you do recall, because you need that for the exam. And what we have here is this red formula. So use formula, and this formula was here. This is the formula we're talking about. I'm not going to highlight over it because you might not be able to see. What do we call the S0? We call that yellow. All right, so that's what that generic formula was talking about up top. So what does this formula mean? Well, the n value is 6, so Sn we replace with 6. So SN we replace with 6. So the N now turned into 6. What does that mean? Just means 6 days. So how many trucks are in each depot after 6 days? Well, the transition matrix, let's highlight this in green. The transition matrix just tells us the probability or the likelihood of where each truck is going to end up. And we power that to the number of days we're talking about, which is 6 here. Right, so 6, 6. Again, people always forget this power. Don't ever forget this power. I'll even highlight it. There we go. And then the S0 is the information we were given, but we had to convert that into a matrix. So depot A, why is 40 at the top? Because depot A is the top one, depot B is the bottom one, and it says there's 40 trucks in depot A, so that's why 40 is up top and 100's at the bottom for depot B. And so this is our S0 matrix. And all you have to do now is just input these, so the right side, into your CAS calculator. Again, if you don't know how to find the power, press the triangle hat or the little up tippy hat next to X squared. And then, well, you got to do that after you've created the matrix, of course, and then that'll get you the power. Multiply it with 40 and 100, and boom, your CAS will spit out your S6 answer. So this answer here, the number at the top is how many trucks are going to be in depot A. Again, because based on the transition, we know the top row is depot A after, well, at the start of the next day, and B is the second row. Okay, so 88 trucks are going to be in depot A at the start of the next day, and or after day 6, and 52 are going to be in depot B. So after 6 days, we have to write out our statement, because in the SAC, it'll expect us to explain what we figured out. If you just have a matrix and you don't know what it means, there's really no point in doing the whole exercise. All right, so after 6 days, let's keep highlighting since we've got the highlighting consistency. After 6 days, 88 trucks will be in depot A. 52 trucks will be in depot B. And to finish it off, let's just highlight those two values so we are aware of where we got them from. Questions, confusions that you guys might come up and think of. Generally, you just need to make sure you highlight and underline whatever works for you. The key details in the questions, especially in the SAC when people are rushing, you got to make sure you're reading the question properly. And that's one of the other things, like don't rush, take your time. Not too much time too, because you might fall behind. Now, the next question says, how many trucks are in the depot after 10 days? So first we figured out 6 days. Now we got to figure out how many trucks in each depot after 10 days. Same process. Our blue is now 10. And so our Sn, our t to the power of n are all going to be 10 now instead of 6. So I'll just go ahead and highlight the working. So what you do is you write the formula, Sn equals t to the power of n times the starting matrix S0, which is the 40 on 100. Okay, so this part is identical to the part that we just did in exercise example 1, part A. And this transition matrix, what color do we have that? That transition matrix was the original one from the top, and that's green. And our power is going to be the context that we're talking about, which is 10 days. So after 6 days, we know the answer, but after 10 days, well, we just plug in these values and put the right side into your CAS. And if you multiply the two matrices with the power on the transition, you'll get 98 and 42. Once again, 98 trucks will be in depot A because it's at the top, and we know depot A is in the top row. And 42 trucks will be in depot B because, well, Depot B is in the second row. So after 10 days, we can expect 98 trucks will be in Depot A and 42 will be in Depot B. Questions you might get, again, your people will definitely forget the power. People will not realize where to get the S0 value from. People will get confused with maybe the N value that you input. All right, so just refer back to the highlights. I'm trying to think if I can make this any clearer. Remember the little 3 dots just means therefore. So therefore after 10 days. It's just a math shorthand, not very critical to your working out, but for formal notes, they are important. Long-term trends. I'm a bit hesitant to read all this because sometimes when students see more information, their minds explode. So we're going to skip past this. But basically, the theory of long-term trends is after a certain number of day or week or year, things stop changing. Or one depot or one warehouse, whatever it might be, will have all the storage of the trucks, and the other depot will have no trucks in their storage. So that's sort of what long-term trends is talking about. And we're going to take a look at an example. So just like shopping centers, you know, if you have Chadstone and what's a crummy shopping center? Manor Lakes Plaza, right? Obviously, actually, no, that's a bad example because it's in different areas. Let's say you've got, I don't know the area too well either. Let's say you've got the Plaza, Pacific Werribee. The only other shop I really know around here is Manor Lakes. So let's say you're comparing Manor Lakes Central to the Plaza. To start with, maybe things are going well at Central, so there's like an even distribution of the amount of people going to the Plaza and Manor Lakes Central, so it's like a 50-50 split. But as the years go past, after 10, 20 years, maybe Pacific Werribee is just way, way better, and the long-term trend is going to be more people are going to flock to the Pacific Werribee because there's just better items, better brands, better shopping variety. And maybe Manor Lakes Central will go under because of the progressive loss of clients or shoppers. So that's sort of the best way I can explain long-term trends. Okay, you might have one that dominates the other completely to the point where it just becomes extinct. Other times you might have a situation where things even out, and it could be what's called a point of equilibrium. If you've done commerce or if you are a wordsmith and you know what equilibrium means, equilibrium means balance. So sometimes, let's say Pacific Werribee, Manor Lakes Central, let's say this time Manor Lakes Central didn't go under, but Pacific Werribee is still way larger than Manor Lakes Central. You can expect more people to rock up to Pacific Werribee, right, than Manor Lakes Central because it's larger, it's got more variety. And let's say the distribution of shoppers is 50,000 to 30,000 each week. So 50,000 that go to Pacific Werribee, 30,000 that go to Manor Lakes Central. After a number of years, people become loyal to sort of their area, and it'll sort of even out. So maybe after 5 years, Pacific Werribee will have 70 or 55,000, and Manor Lakes Central will have 25,000. So Pacific Werribee increased by 55,000, Manor Lakes Central decreased by 5,000, and then that stays the way it is for years and years and years. Okay, so that's what the equilibrium state is talking about. There comes a point where, for some reason, no one knows why, but people have developed the habits and they're just going to go to whatever they feel is routine, and the numbers will stay the same. And you see this in population, you see this in a lot of things. And long story short, there's a person called Mandelbrot. This isn't part of the curriculum, but Mandelbrot actually figured out a set of numbers which which follows these rules, and no one knows why. Okay, so why is it that we all know rabbits populate a lot, right? They screw around and they have a lot of offsprings, but why is it that the whole world isn't dominated by rabbits? No one really knows. They hit a point of equilibrium where even though they produce more offspring some years, other years it balances out. And that's sort of what equilibrium is talking about, balance. Enough of that gibberish. We'll come back to the grey generic formulas, but let's take a look at the examples. I think this is probably the best way to learn. So using the same example from example 1 or work example 14 in your textbook, we're still talking about trucks here. We're still using the same transition matrix. Now, at the start of this day, there were 40 trucks and 100 trucks, which was consistent to what we had before. And this is still our S0. Part A of the question says, in the long term, which depot will have the what happened to the rest of the question? Give me a second, guys. Right, so this here should say more trucks. We'll have more trucks. So in the long term, which depot will have more trucks? Just a side note, if you don't know what a depot is just a warehouse where the trucks are stored. Probably should have mentioned that earlier. But if you don't understand words, maybe also take the initiative to Google them too. I think that's legible. So the way you figure out which depot is going to have more trucks is by this generic rule. You compare the bottom left to the top right. Why? Because if you see here, so the number of trucks that start in A and end up in B is this bottom left value, and the number of trucks that start in depot B and end up in A is the top right value. Okay, these two values or percentages will tell you the movement between the depots. Now, if we color code the top left in light blue and the bottom left, sorry, the top right in light blue and the bottom left in lime green, whichever number is higher will tell us whichever depot is going to end up with more trucks in the long term. So here we've got row 2, sorry. I mucked up the color scheme. Sorry, guys. Lime green's this one. So we still compare top left to bottom right. This is terrible. Top right to bottom left. Okay, so row 2, column 1 is 0.05. Right, so there's a 5% chance of trucks starting at depot A and going to depot B the next day. There's a 15% chance that a truck will start in depot B and end up in depot A. So we know that this value here is substantially larger than the value in blue. And this means that there will be more trucks that end up in depot A because we're looking at the row. So if this value in blue is higher, that means more trucks will end up in depot B. But because the value in green is higher here, more trucks will end up in depot A. And it doesn't matter whatever transition matrix you get. If you ever see long term, you compare. So if it says in the long term, whatever context it is, you always compare bottom left to top right. Whichever one is higher will tell you which one will have more in the long run, and you base it off the row. Okay, so if the top right is higher, it's always going to be the top row, whatever that context is. And if the bottom row is higher, it's always going to be the bottom rows, whatever the context is. Here we're dealing with depots. Just trying to think other questions you guys might have. Why is 0.15 larger? If you just scribble out the 0 before on the left of the decimal place, you'll know that's 5% in blue, and this is 15% in green. So you can always times it by 100 if you're not sure. B, how do we know there will be an equilibrium state solution? If there are no zeros, this is the part I want you guys to underline. If there are no zeros in your transition matrix, there will be a point where there is complete balance. All right, what does complete balance look like? We're going to take a look at that in examples C and D and E. But if there is a value in this transition matrix that is 0, not 0.85, 0.05, or 0.00001, if it's 0, okay, there's no equilibrium. But because there's no 0, we don't have a 0 here, there is an equilibrium. There is a point of balance. And we're going to look at that next. And then if you guys want to read back, that's sort of what these paragraphs are talking about. So I'm hoping my example explanations have solved those 2 pages. But if they haven't, please send through an email. So part C, how many trucks can we expect at each depot after 29 days? Aha. So this is basically what we did in the first example. This is our S0 that we color coordinated in yellow. Our N, which we had in blue. And our formula that we are so familiar with, hopefully by now. So how many trucks can we expect? Well, if our N value is 29, we got to replace everything that's got an N with 29. Our transition matrix, I think it was green. I'm pretty sure it was green. Okay, we had in green, this was given to us at the beginning up top. All right, so transition matrix. Keep the color coordination going. Now that sort of clashes. Well. And then our starting matrix, S0, is what we had in yellow. You input this right side into the CAS, and what you get is our answer, which I think I color coordinated in purple. And what we see is after 29 days, we can expect 105 trucks in Depot A, 35 trucks in Depot B. So you got to write your little statement. Tedious stuff. But once again, in the SAC, it's important because everything are worded problems. And remember, the SAC's in week 8 on the Thursday double. And if you can't explain what you figured out in words, well, then that's defeating the point of further maths. So keep in mind, this is 29 days. And keep in mind, we're talking about equilibrium, which is part B. Remember how we said there's no zeros in our transition matrix. So there is going to be a point where there's an equilibrium. Well, let's see what happens after 30 days. Dun, dun, dun. No spoilers, so we'll scroll down for the anticipation. Here's our formula that we've come so accustomed to now. So whenever we see an N, we replace it. Whenever we see the transition matrix, we know that's one that we were given at the start of the question. I missed the indice. And we know the S0 is also part of what was given at the start when they said, well, there were 40 trucks initially in A and 100 trucks initially in B. And so you input that into your calculator to get 105 and 35. Is that familiar to you guys? If you answered yes, you are spot on. Where from, you ask? Or if you know, well then, if we look back here, it's exactly the same answer. After 29 days, we had 105 trucks that ended up in Depot A and 35 trucks that ended up in Depot B. But after 30 days, we still have 105 trucks in Depot A and 35 trucks in Depot B. Are they the same trucks? We don't know. We don't really care. But what it shows you is complete balance. And we can assume safely 31 days, it'll still be this distribution. 32 days, still be 105 to 35, Depot A to Depot B. 33, 34, 1,000 days. All right, why? If I knew why, I'd win a Nobel Prize. Okay, that's sort of the way the Mandelbrot set goes. We can't quite explain this equilibrium other than Depot A is just more popular. But why does it just hit this point where it doesn't change anymore? Yeah, no one knows. Hopefully we'll figure it out in our lifetime. So part E says, use your answer to eliminate the equilibrium state matrix. In other words, what is the equilibrium state matrix based on what we found above? Well, what we found above was days 29 and days 30 had the exact same answer of 105 and 35. So we can assume this is going to be our equilibrium state matrix because of the lack of change between 29 and 30. Now, between 30 and 31, 31 and 32, there might be subtle changes of 1 or 2, but it'll usually bounce back to 105 and 35. Okay, again, no one knows why, other than Depot A is clearly more popular here. And so the long-term trend we can establish is Depot A will always have approximately 105 trucks, and Depot B will approximately have 35 trucks. I'm just trying to think what I've missed and the questions you guys might have. I've color coordinated everything to the best of my ability. Except for the T. I think that's it, guys. That's yeah, I think that's literally it. So have a go at exercise 9.5. Let me know if there's any difficulties, and if you can think of any questions, please send them through. I'm sure other people do have that same question as well. This is all for the double. Thanks, guys.